have to use this mic.
고이치 하마시다
Okay. And this is,
기업에서는
okay.
일본
Yes,
교토비아에서
but you must use this one.
기계공학으로
Okay. Thank you.
1980년 아사히카세이마이크로디바이스에 있어요. 베타 시그마 ADC와 DAC의 시모스 LS의 설계를 담당하고 있습니다. 현재 아사히카세이마이크로디바이스의 최고 기술 책임자로 재직하고 계십니다. 오늘은 포토브로디오에서 PC, 홈티어럴, 카우디오 전문 스튜디오 레코딩에 이르기까지 다양한 분야에서 하이파이 오디오 베타 시그마 ADC와 DAC 기술 트렌드에 대해서 강의를 하도록 하겠습니다. 고이치.
Thank you, Chairman. 안녕하세요. 처음 뵙겠습니다. 저는 하마시타라고 합니다. Thank you. Now I will talk about the Sima ADC and DSC for hi-fi audio, and also next trend for high frequency area. This is today's agenda. As an introduction, I will just talk about role of ADC and DSC, and why the Sima for hi-fi audio is suitable. And two points I will pick up technology side. For audio band, key points from our development history and products. And also for next trend, wideband delta SIM modulator for RF applications. And finally, conclusion. Now we are living in real world and using digital players or so we are using digital devices and also using IT world for communication in the worldwide. And between digital player and real world, we need analog players, just like microphone or CCD or CMOS image sensor, and amplifier and filter, and then A-to-D converter. Again, playback side, D-to-A converter and analog components and speaker or video monitor is necessary. And also a lot of clocking is needed. Our company is mainly focusing on these analog players. So let me show short about analog signal versus digital signal. Analog signal is continuous time signal in real world. So we have to get small signal and reject environmental noises. And digital signal is discrete time and quantized signal in digital world. So there is a Nyquist theory. So signal bandwidth is limited to fs over 2. And quantization noise is limited to 6n plus 1.8 dB, n is a big number. So main players is again here, and I will focusing on ADC and DSC because this is interface between analog to digital. Previous? Okay. So, yeah. And another area, another role of ADC and DSC is for RF communication. So, in the RF communication area, the data is communicated by a RF carrier. So, data is modulated and then transferred on RF carrier, and then on the other side, demodulated. So the transfer wave is again continuous time wave. So players in the RF transceiver is transmit side is D-to-A conversion, IF filter, up mixer, and driver and power amp, and then go to antenna. On the receiver side, from antenna, LNA, SAW filter, down mixer, IF filter, ADC, and ADC is used. So for this area, ADC or DSC should be wideband. For example, WCDMA is 2 MHz bandwidth, and new long LTE is 20 MHz. So about, I want to show why the Sima is suitable for hi-fi audio. this is ADC architectures. One is delta sigma for high accuracy, and for high speed, flash or pipeline is used, and for low cost but mid speed is SL type. In case of delta sigma, this is basically closed loop type. So we use noise shaping technology with high oversampling ratio. So we can get high accuracy with a few bits, just like more than 90 dB with only 1 bit. And because of high oversampling ratio, so the signal bandwidth is very narrow, divided by OSR. But by using high OSR, we can relax anti-aliasing filter. And we use digital decimation filter. This can reject perfectly outband noise and also generates 16-bit PCM data from only 1 bit. So the performance is perfectly linear performance without no calibration. In case of flash, normally it needs, in case of only one stage, it needs 2 to nth power comparators. So the performance will be up to 8 bit. In case of sub-ranging type, pipeline, n-stage type, 1 op-amp plus 2 comparator is for 1.5 bit MDAC. So n-stage multiplied should be multiplied. In this case, again, mismatch and gain error limits ENOV, maybe around up to 12 bit level, 70 dB. So a lot of person is working for more high speed, for example, 250 mega or 500 megahertz sample rate. In case of SAR, this is low cost, but we need n cycle for n bit conversion. So fs is divided by n. 1 comparator plus n bit that. So very low cost for 12 bit, but very expensive for more than 16 bit. In case of D2L conversion, delta sigma is also same to ADC side. Only difference is digital delta sigma is used and DAC is a few bit plus iron pulse filter is used. These are same, and 1 bit DAC is perfectly linear, no mismatch. Now, sometimes we will use multi-bit, few bit with DWL, data weighted averaging technology. So this technology will do mismatch to average out. And digital interpolation filter is also used. This rejects mirrors in digital domain, and then relax the unknown pulse filter. Current steering is for high speed. The current steering, a lot of current steering is necessary, just like flash ADC. So component mismatch limits ENOV around 10 to 12 bit. R is old process technology, but large R will limit the speed. So next is for audio bands delta sigma technology. We have more than 20 years career in delta sigma area and leading hi-fi audio markets from low end to high end. In case of low end, our target is portable or consumer and minimum 90 dB and low power or low voltage or low cost or multifunction is target. And mid class is home or car application around 100 or 110 dB level. And high precision with minimum cost is important. For high end, there is professional use. This is necessary for studio recording for CD master or something. So studio recording mixer needs more than 120 dB level. And also, these days, DSP plus codec is also used. This is used for Dolby Surround or hands-free talk in the car. So this is just a look of our technology history in the conference, and I'll pick up 5 articles later, next. Before that, this is just show simple delta sigma working principles. here comes the analog input, and there is a loop filter and 1-bit comparator, and then 1 bit is output. The oversampling is, in this case, 64 times. And 1 bit data is D2A converted and fed back to analog input node. Then here is a quantization noise is input here. And the quantization noise spectrum is just like this. If we have enough high gain in the low frequency, then the quantization noise level becomes very small. And then digital decimation filter perfectly cut off this high frequency quantization noise and then decimate it to like FS. This is the okay, next. So this is our fourth order single loop 1-bit type data signal HD, 1988, 23 years ago. Before this chip, everybody thought one delta signal loop should be until 2 second order because oscillating. But this is very nice. There is 4 integrators and feed-forward coefficients from 1 to 4, then adding and 1-bit quantizing, and also using feedback gain, and also using zero insertion in the signal band. Then we can control the stability. So we've got with A-weight 96 dBA and SMDR 93 dB 8D converter. And the output is 1 bit, so the output 1 bit means plus full scale or minus 1 full scale. So inherently linear. Between plus minus full scale, all data is calculated by digital filter. And this type is 3 micron process, very old. Plus minus 5 volt is used, and digital filter was another chip. So this is the performance. These are by simulation, and signal is here, expanded just like here, and we can see zero. This is signal, from here to here is signal band, and these are large, big quantization noise. And after digital filter, 1/64 decimation, 16-bit output. SNR is 96 dB, and SND is 93. These are flicker noise, thermal noise, and a little flicker noise, and second harmonics is minus 100 dB level. So for portable audio, we need more cost down, keeping 90 dB and 90 dB for DAC. So this is the first stereo codec in the world. Left side is ADC, right side is dark section, and this side is analog. This side is digital. 2-channel analog data signal modulator and digital decimator. And for dark side is digital interpolation filter, and after 8 times oversampling sample holds, sync function is also used for filtering. And digital data signal. And 1-bit data comes in, and 1-bit dark plus analog pulse filter is done here. So digital filter is on chip, so we have to change to fully differential circuit. This is simple. This shows a fully differential circuit. So we can cancel digital noise and even harmonic source. And SNR, we can get 3 dB more because signal is plus 6 dB and noise is plus 3 dB. And in case of feedback lag, we can do positive or negative. So simple selection or plus minus selection can be done. On the other side, the dark side, the fourth order modulator is changed to digital side. So integrators is changed to accumulators. And 2-channel timeshare is very easy. 2 registers is added here. And there is also inserted. After 16-bit data comes here and 1-bit data go out here. This 1-bit data comes here and simply 1-bit dark is done by path selection. And bycast filter is used for post filter. And the second stage is the switched capacitor buffer for real-time interface. So next is the more high accuracy. So we've changed to fifth order 1-bit type. This integrated is added. So, and also we can put the two conjugate pair 0. This is the performance result. These are simulation and 2-0 can be inserted. And 18-bit case, the performance is here, full scale and minus 60 dB dynamic range. Second harmonics is rejected by digital free differential circuit. So this is the 2-2 cascade type. From the consideration of stability, multi-stage is better than single loop. So second order first stage, second order first stage. So 2-2 cascade type is here. And also we put the local feedback to reject overload. So we need not anymore about gain scaling technology. We can get more SNR and dynamic range. The problem of 2-2 cascade type is this is the first quantizer. Quantizer's error, Q1, may be leakage. There is noise cancellation logic here and unknown coefficient here. If there is a mismatch, Q1 will be leaked. But thanks to second order, we can get more mismatch tolerance. This is the performance. In case of minus 20 dB input, we have no distortion and only floor noise. This is the input signal level versus output level. Around here, more than 100 dB SND is possible. And minus 6 dB input and 50 dB SNDR, that means 110 dB dynamic range. This is all process 0.7 microns, or maybe 40% is unknown. Now, for more high end, now we have products 123 dBA, most high one, and SND is 110 dB. We are using DWA plus multi-bit quantizer and cascade technology. And next trial is more 4 dB. This is the R&D result. Floor noise is around 150 dB level. So, final example is that case. This is 120 dB level case. These are total architecture. And digital interpolation filter and 31 level third order digital data signal, and some meta decoding and DWA, partially DWA. And on the analog side, we use 2-tap FIR filter in the analog side on the switch capacitor domain. And first order low pass filter is done by switch SC buffer type. This is the performance minus 60 dB level and gain tracking, and also in this case 4 times of 48K sampling data comes in, and then these are more than 48K, 40K to 80K. We can show a little quantization noise, but the performance is very nice. So in case of 0.5 micron process, 60% is analog. So this is conclusion about audio band. In case of loop technology, there is single loop or cascade loop. In case of single loop, we need to care about the stability, but it is good insensitive to mismatch. In case of cascade, basically stable but sensitive to mismatch. Quantization bit number, if we use one bit, inherently linear, but total noise is large, so we need more high order or high oversampling ratio. If we use multi-bit, we need DWL, but we can get noise is small, so we can get more higher SQNR or dynamic range. About OSR consideration. In case of high OSR, we need high speed in switch capacitor settling or comparator working speed or digital speed. But we can get very nice performance on KD over C noise. We can reduce the noise 1 by OSR. For example, if OSR is 64, we can get minus 18 dB reduction. So about the design side, inbound noise, quantization noise should be low enough. Then the unknown noise can be dominant. Out-of-band noise case, ADC case is digital decimation filter can reject perfectly, but that case that we cannot reject. But not audible, and should be reduced by unknown post filter with some noise addition. So for ADC, every candidate may be possible. Select depend on purpose. But in case of DAC, I think single loop, multi-bit, low order, and also high OSR is better. So next I want to change to a wideband delta sigma modulator. This is a simple diagram for receiver side, antenna and SAW and LNA and down mixer and ADC and IF filter and ADC and remote. Today, a lot of circuit is using pipeline ADC for maybe 50 to 60 dB level, and IF filter is used. The main purpose is to reject broker adjacent to the frequency. So ADC is a key component for receiver side, cell phone or DTV or wireless side. Signal band is from 2 MHz to 20 MHz, and dynamic range is from 50 to 75, and SFDR is more. Those depend on total system request. So if we have wideband delta sigma ADC with high dynamic range, for example, 70 or 80 dB, then we can reject IF filter itself. Broker can be rejected by digital filter. So the system design can be easy and low power and low cost and more reliability. So the question is how to design wideband delta sigma. That is basically narrowband by oversampling. So today's approach is more low oversampling ratio. In case of audio band, we've used 64 times, and now change to minimum 8 times. Yeah. Okay. So, in case of inbound thermal noise consideration, 20 MHz band versus 20K band is 1,000 times difference. This means 30 dB larger than audio band. So wideband 70 dB means 100 dB in audio band. So key points, I'll pick up, there are a lot of key points in this area, but I only pick up these small items. In case of continuous time, it is including anti-aliasing filter, but not FS tracking, and also jitter sensitive. So challenge is jitter insensitivity or process or temperature dependency cancellation or something. And switch capacitor time is now running after. This is all not including anti-aliasing, but relaxing anti-aliasing is same. And FS tracking and jitter incentive is very nice performance. I'll show two types example. And also last month, there are wideband data streamers in CICC. I'll show a little. So this is one example of CD. Okay. This is one example of CTDSM, fifth order single loop type. So we use the GMC type integrator, 1, 2, 3, 4, 5, so fifth order, and 2 local feedback, and total summing, and sampling, and comparison, and 1 bit feedback type. So here, jitter sensitivity is important, so we put switch capacitor DAC plus R, so we can get jitter incentive, because charge transfer becomes small as the final edge of TS. And also, GMC or R is very voltage process temperature dependency. So we put the replica DAC. Then we can use high-speed GMC integrators. And the dynamic range is 71 and bandwidth is 2 MHz. OSR is still 32. This is for wideband CDMA. So this is performance result, minus 3 dB input case and 2 tone case and signal tracking performance, etc. So next is calibration technique as CTDSM. In case of continuous time data stream modulator, everybody is thinking about single loop only, because due to cascade or mash type, there is a very huge leakage of first stage. So we've added calibration technology here. Insert calibration tone here. And this tone generates quantization noise, same to quantization noise of this first quantizer. So noise cancellation logic, the purpose is bunch out of this Q1 leakage. So if the calibration tone is bunched out from D out, then analog component versus digital coefficient is perfectly matching. So this is an example. This is minus 20% difference and plus 20% difference. We can see calibration tone here, and those are a lot of the quantization noise. And if the calibration is matching, the tone is vanished out. And also quantization noise becomes small. This is total one. So next change to switch capacitor type data stream modulator. This is OSR is 24, so output rate is 200 MHz, but we used two separate paths and interleave these. So external clock can be relaxed to 100 MHz. We used both clock rise and fall clock edge. And then the switched capacitor settling requirement can be relaxed from 5 nano to 10 nanoseconds. And also we put one noise coupling path here, blue one. So analog side is second, this side is second order, and also noise coupling adding first order. So total is third order. Then this can be, the result is very nice, SNDR 79 dB, and bandwidth is 4.2 MHz. SFDR is more than 100 dB, and we can see 60 dB per decay, noise shaping. And this is input signal versus SMD. Very perfect linear performance can be seen. And figure of merit is 0.48 micron, 0.48 picojoule. This is 0.18 micron process. So next is double sampling technology. This is also in switch capacitor DSM. So in case of double sampling, we use op-amp 2 times per clock. Normal switch capacitor, we use only half cycle of this op-amp. So phi 1 and phi 2. In the phi 1, this is sampling and this is integrate. And the phi 2 mode, this is integrate, this is sampling. This is double sampling technology. So for the switch to capacitor input side, we use 2 cap. But the feedback jack side, this is same cap. The reason is mismatch can be go to Nyquist in case of input side. So this mismatch can be cut off by digital filter. But in case of feedback jack case, the mismatch will erase down from SS over 2. So this is 1. So there are 2 examples. This is for single loop type using double sampling technology. And the result is we can get 20 MHz bandwidth, but the peak SNDR is only 63 dB. This is not enough. Frequency is very nice. So next trial, this is presented last month. Signal bandwidth is 10 MHz and SNDR is around 74 dB. And figure of merit is less than 0.3 picojoule at 0.18 microprocess. 2-2 cascade and low distortion architecture is used. So on this September CICC, at the theme session, there were 7 papers and 6 papers was the wideband area. And categorized is 3 types is switched capacitor type, and 1 is continuous time, and 1 is LC type. So these are process and figure of merit. So process is perfectly different, 0.13 or 65 or something. And the figure of merit, these 3 is very similar, around 0.3 picojoule. And previous one is also. And technology is perfectly different. Op-amp is stage sharing type, or no op-amp type, 1-1-1 match, or VTO-based counter type for second stage. But amazing is the figure of merit is same. This is 4-bit quantizer type single loop, but using RC integrator, not GMC type. Signal bandwidth is large, SNDR is not enough. LC type is very attractive, RF direct bandwidth. So center frequency is 900 mega and FS is 3.6 giga. This means we can omit RF mixer by digital mixing after ADC. So this is the second conclusion for wideband data signal ADC. So continuous time versus discrete time is, this area is started from continuous time using GMC integrator around from 2000 years. And now moving to RC integrator, if we have wideband op-amp. And switch capacitor is running after just like previous pages. And now covering 5 to 20 MHz band, and also including SNDR. This type is more accurate and FS tracking for mobile use, multiple use. So now, important point is the challenge for more low oversampling ratio. And we can use a lot of type of circuit technology. Those are already proven in conventional switch capacitor circuit area, just like pipeline or etc. Delta signal versus pipeline. Pipeline is not so large dynamic range and also need high order IF filter and ADC. Delta signal case, it has more than 70 dB dynamic range and figure of merit becomes very nice. So blockade rejection can be done in digital side. The new RF direct bandpass delta signal ADC is also very nice. We can omit RF mixer, very attractive for future RF, but LC resonator need tuning, difficult to use for FS tracking system. Anyway, delta signal is now on R&D for more than 500 MHz, but already feasible for 2 MHz area. And changing receiver side architecture for more high performance or low power or good productivity. So this is the final conclusion. ADC and DSC. ADC and DSC is interface between real world and the IT digital world. Audio band delta signal was first introduced in 1988, and now with continuous technology challenge and leading digital audio market for better human life, wideband delta signal ADC will make next innovation in receiver side RF application, and will contribute for better communication in worldwide. Fine process is attractive for digital or millimeter wave, but as you know, it is leaky and low voltage. So for high performance channel, small leakage and high voltage component mismatch is more important. So this is my thinking is designers with some sharp cover the speed drawback of all the process. So we again will continue technology challenge for worldwide human life. This is my final piece. Thank you.